So I was saying that he's an amazing scholar, and he works in India, and he popularized this PAC learning and make it more beautiful by his beautiful lectures. And many people notice that it's something that has not been focused enough, so we can concentrate on PAC learning more in machine learning community. So the proof of this beautiful theorem is like this. First, we say that we write dq dg by this dp. So we multiply and divide. So what happens is that this is the log of dq dp, and the multiplication in log becomes summation. So it becomes a summation of log of dp over dg. But because dp over dg, the log of that is like minus log of dg over dp. So this minus and this minus produces this plus. So we go on, and so this is just KL divergence, no problem. And now we are using this phi. So because we know that KL is positive, it is not negative, so it reaches its maximum when they are equal, when Q and G are equal. And putting this and just solving it for phi, if you just choose, because I said that phi could be any function. So just pick this function, it produces this result. And finally, this is a homework for you, reading this beautiful article and implementing this algorithm. So you see how you do regularization. I mean, a different approach to regularization in neural networks. And you see that regularization is everything, because if you have a function space, for example, all functions that cross these 2 points, this one, if you regularize it, I mean, putting some constraint in your optimization, but we do it in by some strategy, then you can control this function space. So this function space is not a big giant. So I just want to come back and talk about generalization and PAC Bayesian learning. So in the next lecture, I will give you some example for deep learning, in particular for problem of first linear classifier. So next week I will talk about linear classifier. Then I will talk about multi-layer binary networks. I mean, your activation is binary, and we want to see how can we design the weights, how can we train these neural networks so that we have a better generalization. Then another weekend I will talk about wavelet scattering. This is really important, because if you know that in harmonic analysis, I I mean, traditionally we work on Fourier spaces, wavelet spaces, shearlets, curvelet, framelet, all of those things. You can reduce. It's like look at it as a representation. In deep learning we use convolutional neural networks for representation, because if you change, for example, you have an image, a picture, but if you translate it here, it becomes another picture. So or rotate it or deform it. For example, in MNIST data, if you rotate 2, it should have the same representation. The distance in the representation space should not be too much. And that's why people invented, it's like convolution. You're doing it. That's why convolution is very important. But people now generalize convolution to group equivariant versions of that. But what I want to suggest is the work of that French mathematician Malat, Stefan Malat, I remember, that he introduced wavelet scattering in one of his articles. So he proved that if you just translate an image, rotate it, deform it, everything, if you use wavelet scattering, which is completely different from discrete wavelet transform, then that generalization, so that, for example, your image becomes now a vector of coefficient, for example, 252 coefficients that you do after this wavelet scattering, something like this. I will explain it in part 3. And so instead of just writing articles about group equivariant convolution neural networks and everything that is invariant to the transformation and rotation and deformation and those things, we can just use wavelet scattering. And this does everything for us because Stefan Malat has proved that. So we don't need anything. We don't need to worry about what happens if you rotate it or those things, because the problem of those group equivariant methods is that you add lots of layers, lots of parallel neurons, maybe millions of neurons you should add in order to just say, okay, this picture is invariant to translation. But already wavelet scattering. So I predict that in 2032, people use wavelet scattering at the beginning of their deep learning layers. The beginning layers, because you have some layers, and these usually use convolution. So instead of convolution, just use a simple wavelet scattering, and that's it. That's good for representation of your data. And then you give it to anything, for example, a multi-layer perceptron or anything, or even a simple algorithm in machine learning. So that is more effective. And also your neurons is reduced. Although we have 100 billion neurons in our brain, but our brain, Stefan Malat he gave us a beautiful example about our ears, that inside our ears there are something like wavelet transformation. So it is passively implemented in our ears. So it's not the thing that I suggest. It is already inside your ear. The problem of machine learning guys is that they always talk about our head, but even our ear could be a source of inspiration. And it is very beautiful to look at all parts of our bodies. So the next thing is frames and bases. Traditionally, Fourier, in Fourier times, from Fourier times till now, people talk about orthogonal spaces, like sine and cosine. They should be orthogonal. So it's a very hard restriction. And that's why people notice that, okay, you don't need that orthogonality. You don't need even a basis. You can create a frame. And that was the motivation of recent progress in shear leads and many complex transformations. And finally, in part 5, I will introduce meta-learning techniques. For example, 3 of them. For example, mammal, proton networks, and some other algorithm. Some of them are non-parametric, some of them are parametric, some of them needs optimization like gradient descent. But meta-learning is the future because the way a child learns, for example, one day we teach him or her, we teach, for example, different types of cars. Look, that is a beautiful car is passing. Look, that is a beautiful bus. And the next day, for example, we go to the jungle and we talk about animals. We show him a lion, we show him a dog, we show him a cat. And the next day, for example, we go somewhere else and we teach how to ride. So everything about cycling and those things. So we are doing it step by step, and it needs priority. For example, if a person cannot do a simple multiplication of numbers, for example, 2 by 3 becomes 6, then we should not give him a new task like, for example, Hilbert transform of a function. So that's a complicated. So the learner cannot learn new things. The learner, the supervisor, the teacher, should create a priority over tasks, saying that, okay, first we should learn basic mathematics, and next year we go to intermediate mathematics, and then you gradually increase the complexity of what you are learning based on what you've learned before. So it's just an epsilon perturbation of what you have learned before. That's why the learning is very fast. So we want to mimic this idea and put it on meta-learning, putting for meta-learning. So meta-learning is the future of machine learning. And finally, in part 6, I want to generalize PAC Bayesian for the meta-learning. Although this is poorly understood, because even PAC Bayesian in the simple traditional machine learning is really hard, but it's a very it is still in its infancy using PAC Bayesian for meta-learning, because you're producing tasks. You're in the task space. It's not just data points. It's a task point, different tasks, 1 task, 2 tasks, and you have different M tasks. And that's why it becomes hard, because function space is already hard. You put function over function space, so it's very complicated. And finally, I will talk about semantic hashing. And in particular, I will use mutual information. If you have watched my lectures on information theory of deep learning, mutual information plays an important role in unifying machine learning, because it is related to probability theory, and probability theory is the most natural thing to see the relationship between random variables. So that's why it's very important. I think this is enough for this weekend. Next weekend I will start PAC Bayesian for deep learning. Lots of examples showing that they are not just mathy objects that people don't like. And you can use it, even practitioner. I invite all of the practitioners to apply PAC Bayesian for deep learning in their companies, because they can create a better generalization to show it to their boss. So thank you very much. That's enough for today.